I guess I'd like to start off with maybe shaking the pot a little bit, right? The phase diagram that she showed for cerium bismuth is wrong, right? Because we're just about to publish a new binary compound in cerium 3 bismuth 7 that exists in that phase diagram, right? So I'm a chemist, right? So it's always a challenge to speak to physicists, right? Because we see things different, right? So for you guys, the prices on the properties, for me, for a friend, probably, right, the price is always on the, something new, something nature did not have a chance to see, something that no one has seen before, right? So what I will talk about today, right, is how I view, destruction and bonding, right? And, the technical details and how to make, things I'll leave, for, a later talk, right? So, first things first, right? Now I'll still have your attention, right? Because I'm pretty sure after 5 slides I will lose you, right? So this is the take-home message, right? So, someone much smarter than me, right? This is Linus Pauling in '92, right? He died 2 years later, right? By that time he had already 2 Nobel Prizes under his belt, right? And he was still fascinated with bonding intermetallics, right? So, and unfortunately, right, in year 2018, right, this is still true, right? We don't know, right? Bonding in oxides, maybe. Bonding in chalcogenides, halides, coordination compounds, organometallics, yes, right? Bonding in intermetallics, I will show you in a couple of slides, right? It's still up in the air, right? And if you don't understand bonding, right? If you don't understand structure, right? All this talk, how you're going to synthesize something, right? Is completely redundant. Right? And this is where I'd like to take a moment, right, and acknowledge someone, right, who really inspired me, right, and he's my academic grandson, right, father, right, I'm his grandson, right, so who is now not with us, right, and Halyana probably had the chance to meet him while at Ames, right, so John Corbett, right. This is the most important take-home message from my presentation, right? So, we need imagination, right? To make new things, to make those compounds that are not in the binary phase diagrams, that are certainly not in the ternary phase diagrams, right? We need to do synthesis and we need to have imagination, right? And well, fortunately, imagination comes with experience, right? And if, to build experience, right, you also need 3 important things, right? In real estate, right? Those of us that bought homes in 2005, right? And still suffer, right? But when I was home shopping, right? The realtor told me there are 3 important things in real estate, right? Location, location, location. Right? In synthetic chemistry, right? I would argue that there are 3 important things, and they're not location, right? Location might be important, right? But atomic sizes, electronegativity, and the most important thing is the number of valence electrons, right? Where elements are in the periodic table, right? And I will show on a couple of examples how this comes into play, right? So now we saw the periodic table before, right? So this is beyond the general chemistry level, and I apologize for this, right? But anything in blue, right, is a metal, right? I already made a point that the bonding in metals and intermetallic compounds is still poorly understood, right? So those are the things that we will not be talking about right now. But, right, and this is I don't mean to sound derogatory, right? But even at Ames, right, when they certify their metals with 5 nines, right, they certify the blue stuff. Right, which means you buy, ceriums with 5 nines that has been electrophoretically purified and whatever, right? They tell you that it's 9.999 cerium, right? But they cannot certify oxygen, carbon, nitrogen, and other things in it. It's absolutely critical, right? Because in many binary compounds, right, it turns out that these non-metallic elements occupy interstitial sites, right? They're actually pseudo-binaries, right? So even if you make the same compound twice and you measure the properties, right, you would be amazed sometimes. Same person, same furnace, same elements, right? 2 different properties, right? Simply because you might have introduced a small amount of oxygen or carbon or silicon or something else, right? Which unfortunately, the analytical techniques that are available to us, right, they will not be able to quantify. Right, so these are very important things, right? And this is where understanding structure and bonding and how to count electrons is actually very important, right? I rarely get to lecture about this stuff, right? And because I figure that most of you will be physicists, right? And you may not have appreciation for what the chemists do, right? And how this whole thing exploded, right? So the main technique for studying intermetallics, right, is diffraction, right? So people have known about compounds between metals for a number of years, right? But look what happened after the Bragg and the son and father discovered X-ray diffraction. This whole thing exploded, right? Because before, right, there was really no good way to study intermetallics, right? They would be making compounds, right, and they will be doing aqua regia and other tests, right, to find out whether something dissolves faster than the starting materials, right, and then they will try to deduce some type of composition, right? No structure, nothing, right? 97, right? Helena showed the Pearson-Hearn book, right? About 20,000 compositions documented, right? Known, right? And I say known, right? Because in the past year, right? And this is probably about half a dozen of those contributions from my group, right? And I already alluded to, right? We are just about to publish on two. Right, it's not just the cerium, right, and the praseodymium and neodymium too, right? 3-7 compositions in the binary phase diagrams of rare earth and the bismuth. So this is still happening, right? This is year 2018, right? The materials genome project is already up to full speed, right? There are websites where you can go in and click on the periodic table and they calculate for you phase diagrams, properties of known compounds, and this and this. Yet, people like me go in the lab, right, and we continuously making things that should have been discovered half a century ago. Right. Again, chemists versus physicists, right? So alloys and compounds, right? So there was a fine print in one of your slides, right? What is a line compound? There's no line compound, right? So all compounds have finite stoichiometry breadth, right? So even the cerium and the copper 2, germanium 2, right? Is not 1 to 2, right? There's always 2x minus x, right? But the biggest difference, right? Alloy, right? Which you would find in many physics texts, right? Is not 1 to 2, right? Alloy is just a solid solution, right? So the compounds usually have a composition, something that's defined, right? That happens within a specific structure, right? There is also very big importance on this bullet here, right? Atomic interactions in compounds are specific. There is some directionality, right? With alloys, right? They just freeze things, right? So there's short range order here, right? And of course, to me, right, the biggest difference between alloy and compound, right? When I form a compound, right, the properties of what I made, right, are vastly different from the properties of what I started with. Right? So, for example, you can take copper and zinc and fuse them together, right? You can make a continuous solid solution of things, brasses, right? They have different properties depending on how much copper and zinc you have, right? But in some way, right, the brass properties are somewhat intermediate between the properties of copper and zinc, right? If I form a compound, right, as we saw in the example of cerium 4 bismuth 3, right, the melting point is 5 times higher than the melting point of the two components. All right, and again, this is something that everybody should be familiar with, right? And I apologize if I'm, diluting my talk with a surplus in a slide, right? But this is, the ABCs, right? So, electronegativity, right? So chemists understand this intuitively, right? Electronegativity is an empirical concept, right? This is the ability of an atom, right, to attract electron density to itself. So essentially, this is how I measure the bond polarization. This is how I understand what becomes anionic and what becomes cationic. Right? How the electrons move about the crystal structure. Right? Of course, if you have molecules of the non-metallic elements, right? We have homoatomic, classic, bonding, sigma and pi bonds, right? As we increase, the electronegativity difference, right? We form extreme in the case of polarization, which is ionic in a bond, right? Along this line here, right? We also have ionicity, right? But these are the salts, right? If you think about, for example, sodium chloride, magnesium oxide, etc., right? And of course, as the elements become closer and closer in the periodic table, the electronegativity difference becomes smaller and smaller, right? So now we end up in the realm of compounds that would be essentially lacking any directionality in the bonding, right? Just alloys, right? And of course, the interesting things for chemists happen here, where you have a mixture of all three, right? So when we talk about ionic bond, when we talk about polar covalent bond, right? These are just the extremes, right? The reality is that things are happening somewhere here in the middle, right? And again, with electronegativity, right? There are many different scales, right? Electronegativity is empirical, right? This is the Pauling scale, right? The most commonly referred to scale, right? So the metals in the left part have low electronegativity, which means that they are very willing, to donate electrons, right? These guys here, the non-metals, are the ones that are with high electronegativity. They are likely to accept electrons, right? Notice what happens here, right? So this is something that's not appreciated, right? The electronegativity of gold is about the same as the electronegativity of carbon, right? So there's a compound that is known as cesium aurite. Cesium is here, gold is here, right? Cesium aurite has the crystal structure of cesium iodide. Cesium aurite is transparent, red, right? Because what happens is cesium donates electron to gold, just like cesium donates electron to iodine. Same crystal structure, same way I would think about it, right? Right. And of course, this compound, cesium aurite, was discovered in 2004, right? Should have been discovered in 1904, right? And it should be no surprise to anyone, right? That this happens, right? But again, there's a talk about doing hydrogen activation and catalysis, with non-noble transition metals, right? Well, here's hydrogen, right? Here's platinum, here's gold, and here's iridium, rhodium, right? So the electronegativities of those are well matched, right? This is why the chemistry works, right? And if you try to do it with iron, right? Iron, cobalt, you just have to find a good compound that will change the electronegativity, right? The electronic structure of the metal, right? So then the whole thing will work, right? This is why organometallic chemists are making strides, right? Now where the heterogeneous community, right, is still stuck with just the elements and probably trying to figure out a way to nanostructure known metals, right? But that's a separate subject, right? So let's talk about phase diagrams, right? I'm not going to show the phase diagram right now, but let's say right now we know that there's a base in a line there, right? Now there's a the simplest possible reaction that one can do in a known phase diagram, right? I chose something that's less trivial. One equivalent sodium and one equivalent silicon, right? So the structure of the metals, right? The alkali metals, have either body-centered or face-centered cubic structure, right? Group 14 elements, silicon, right? And it has a diamond structure. Okay. We fuse them together, right? Now again, the phase diagram is available to us. We know at what temperature this reaction should happen, right? This is a congruently melting in a phase, right? That's the highest melting in a compound. Good luck growing this out of flux, by the way, right? Because it's very air sensitive, right? And it's very unstable. But when you find a way to grow crystals of it, right, and you subject the crystals to X-ray diffraction, right, you find out that this is what happens. Right. The structure is completely different, right? So this is the sodium, this is the silicon, right? So the bonds between the sodium and the silicon are not shown, right? Because I would think of those bonds as being electrostatic, right? Only these bonds, which are shown with the cylinders, are what I would consider as covalent bonds, right? And this is how we'll partition the electrons, right? So before we go in that structure, right? The sodium chloride, right? Again, the sodium is electropositive, chlorine is electronegative, right? Donates electron, accepts electron. This becomes a noble gas. This becomes a noble gas. Right? In this compound that I just made, right? I have these units. Right? So what I'm going to say is that I reduced silicon. Each silicon accepted one electron, right? And silicon was forced to form a tetrahedron, right? And now I'm going to call this a silicon 4,4 minus, right? And then I can recall, reading in Wells's book that, oh, wait a minute, white phosphorus, naturally occurring in a form of phosphorus, right, exists as a P4 molecule. It's neutral, right? So essentially, what you are doing is, right, you're taking silicon, right, and you're putting one electron onto silicon, and you're forcing silicon to behave as phosphorus, right? So what happens here is, right, sodium silicide, right, is now rebranded as sodium 4 silicon 4, right? So now I have 4 cations for each of these species, right? So this is silicon 4,4 minus. Sodium achieves noble gas configuration, right? And now I'm forcing silicon minus to behave as neutral phosphorus. Okay. So this is my very basic introduction on how I count electrons and how I think about bonding, right? So right. So physicists don't need an introduction to those structures, right? Because this one in specific, right, has become subject of many discussions, right? This one is probably also well known, right? Among the two 1 to 2s, right? There are probably over 2,000 examples, right? 2,000 includes different variations and solid solutions, right? Well known, right? So this is a trigonal called calcium aluminum 2 silicon 2, right? Now this structure in many books is also referred to the inverse of the lanthanum oxide, right? Or there is a ordered version here, which is lanthanum oxygen 2 sulfur, right? So there's a bit of a variations there, right? But the important thing is, right? That's a compound, right? And it has a fixed number of valence electrons that make that structure happy, right? So for example, this compound here, which we have made in my lab, right, is one of the many, right? One way I would count the electrons is I would say calcium, again, being the most electropositive element, donates electrons, right? So calcium has only one stable oxidation state, and it has to be 2+. Antimony accepts the electrons, and it becomes antimony 3 minus, 6 charges, right? Then, to balance things out, right? We'll need to have manganese and oxidation state in the +2, right? Or D5, right? Because this is now manganese in a tetrahedral coordination in a very happy, very stable, form, right? Another way to look at this, right? Now, this is a 16 electron per formula in a compound, right? Almost all examples of compounds adopting this structure, this is a layered structure, right? Have 16 electrons. Right? 2 times 4, 2 times 3 plus 2, right, is 16. Right? So if you count it here, excluding the D electrons from the manganese, same. Okay. So with this case here, the situation is a little bit more obscure, right? Because there are 2 forms of thorium chromium 2 silicon 2, right? One is what physicists call the collapse structure, right? Where those 2 layers come in close contact, right? So then now there's some type of bonding between apices, right, along the trigonal axis, right? So the electron count here will be also 16, ideally, right? But if the structure collapses, right, the electron count will be reduced by 2, right? Because those 2 layers, right, will be sharing 2 electrons between each, right? Again, the electron count is 16, right? So notice that this is calcium manganese antimony 2. This is barium manganese antimony 2, right? If you're paying attention, right, I told you that there are 3 important things to consider, right? Electronegativity, sizes, right? Number of valence electrons, right? Since the calcium and barium are in the same unit group, right? number of valence electrons is the same, right? 16 electrons per formula, 16 electrons per formula, right? Manganese in this structure, right? This 2+. Manganese in this structure is also 2+, right? This has been proven by susceptibility measurements and has been proven by DFT, right? So there's no question that this is not part of the equation, right? So what's left is either the small electronegativity difference between calcium and barium, or, most importantly, right, the larger difference in sizes between the calcium and barium, right, because as we go down the group, right, the atomic sizes increase, right. So it turns out that in this case, here, right, we are crystallizing, the compound with this structure because barium, right, is just too big, to pack efficiently, with manganese and antimony in that structure. Right? And this happens very frequently, right? In the chemists, right? We look at the periodic table, we exploit the periodic trends, right? And this is one of the tuning knobs, right? And if we need to make a variation in a structural change, right? Chemical pressure, if you wish, right? At some point, right, the chemical pressure will be so high, right, that the structure will no longer be happy, right? So that's something here. And of course, there are many examples of, this and this being, in equilibrium at some point, right? But that's part of a separate discussion.
So, Svilen, I have a question.
Yes.
Going back, you said when you did the 16 electron count, you ignored the D electrons.
Yeah.
So, are you just saying they're going into the metallic mix, or?
Those papers here have addressed that, right? So that structure is adopted by many in a main group in the compounds, right? Zinc, cadmium from the D block elements, right? It's all in the band structure, right? So the D states for manganese, right, are not anywhere close to the Fermi edge, right? Okay. So essentially, they're there, right? They contribute, right? But how you go from graphite like layers, right? How you pucker them, right, to zinc in the blend structure, right? And then how you distort cut those bonds to form those corrugated layers, right? Stuff things in between, right? It's all addressed, right? Gordon Miller and Jeremy Burdett, and then Ralph Hoffman and von Schnering, right? So it's all there, right? It's done, it's analyzed, right? I'm not saying anything new here, right? So of course, those papers have been cited probably a gazillion times since the superconductivity in barium, iron, and arsenic. Because even if you think about barium, iron, and arsenic too, right? So this compound, right, is also 16 electron system, right? And the way that you would change the electronic structure, right, and form those collapsed structures is, right, by either doing substitutions on this side or this side, right, or can substitute the barium which is how originally this thing was done, right? Barium and potassium, right? They almost have the same ionic size, right? But this is isoelectronic substitution, right? Removing a little bit of electron, right? And the forces that to happen. And of course, the preferences here have also been addressed, right? You have the p orbitals, the s orbitals, the hybridization, which element would take the tetrahedral site, which element will take what they call the umbrella site, right? Based on electronegativity, right? And analyzed in beautiful details, right? In a very beautiful work. Right? And back in '86, right? Ralph Hoffman, right? Ralph Hoffman, by the way, has a Nobel Prize in chemistry, right? So he's not someone who doesn't know what electronegativity sizes, right? And all these things actually mean, right? So he put up, he won it in '81, right? By the way, right? So this is 5 years later, right? He put up this table here with known compounds that obey the 16 electron rule, right? He calls rib is this bond here, right? And then he analyzes rib and handle bonds, gives references, right? And I'm assistant prof, right? Reading this paper and scratching my head, right? So a Nobel Prize, winner, right? And he put out these two compounds here. In that, this is not his work, right? He's a theoretician, right? He doesn't make anything. Right? But it didn't cross his mind that these are not 16 electron compounds. They're 15. Right? And I be honest with you, right? The first proposal that I wrote, here, right, got trashed, right? Because I said this is ridiculous, right? All right, so going back, to this, right? So I looked at the known crystal structure reports, right? So with that particular structure, right? For example, this magnesium 3 antimony 2, right? Which is that lanthanum oxygen 3, right? Which is the calcium and aluminum 2 silicon 2, right? There are 372, all were. Now there may be more, right? Crystallographically identified. They're not speculated. They're not someone see, right? There's a SIF for this, right? Someone did the crystal structure. Of those 372, right, there are 4, right, and some of those are the ones that Ralph Hoffman, cited in that paper in 86. Right. Of course, they're published in German publications. It's hard to read, right, because no one knows how to read German anymore, right. So, but luckily I had a German postdoc, right, so she translated everything, right. So we went in the lab and repeated the work. Right, because I just couldn't believe it, right? Right. It has to be 16, right? There are very few examples of 14, right? But there's nothing with 15, right? And I just couldn't believe it. So we didn't spend just 5 minutes on this, right? It was more like 5 years of work, right? Just to prove a point, right? Because I was stubborn, right? So you go in the lab, right? Again, good luck growing this out of flux, right? Because it's it's a project, right? So, but you take one equivalent cerium, one equivalent lithium, two equivalents lithium, two equivalents antimony, right? You put them in a suitable crucible, right? It has to be closed tantalum, right? Because lithium will evaporate, right? So, right? And then this is what you get. Right? And this is the simulation based on the structure. Right? The structure is simple, right? There's no, way that you can say, hey, this is not a good match to this. Right? But then you count the electrons, right? And again, it doesn't work. Right? It doesn't work, right? So then, what you have to do is, right? You have to say, well, if this doesn't work, right? Now maybe. Then this lithium to lithium interaction, right, is important, right? So you draw a stick in between two lithiums, right, and then reviewers come and say, you're crazy, right? You're saying that this is a covalent lithium-lithium bond, right? It's not, right? What happens is, right, actually there is a site, an octahedral site in this structure which is occupied by one lithium. Right? So this compound is not 1 to 2, right? It's 1, 3, 2, right? But because lithium has 3 electrons, right? And you're putting lithium next to cerium, which has 50 some, and antimony, which has 50 some, right? You cannot see it. Right? You have to, really, have a good crystal. You have to have a really good eye, right? And when you do, right, then you identify. The electron density sitting here in the middle of that layer, right? You put lithium there, you refine it, right? Your R value goes from 2.1 to 2.0, right? But the important thing is now you fix the electron count. The chemistry is beautiful, right? Again, this I burnt a graduate student in a life on this, right? But I think we all learned an important lesson here, right? Ralph Hoffman, I don't know if he read this paper, right? But the Germans that published the original structure, right? Now long expired, right? So they probably couldn't care, right? But I think fixing that it was important, right? It's just beautiful, right? If you look at the distances, everything, right? It makes perfect sense, right? It has to be there, right? It's a, now, this is a precedent of what I call stuffed version of that 1 to 2 structure, right? And of course, you appreciate this, right? Right? This is a semiconductor, right? It's boring, right? The analog here, right? Go figure. This is an isoelectronic substitution of cerium-3 for praseodymium-3, right? That is just a Curie-Weiss behavior, right? Which we can, cerium, right? Is always never simple, right? To fit into inverted Curie-Weiss wall, right? But in this case here, right? It's either we have some impurity or something else is happening, right? No, we don't know, right? Those are very air sensitive in the compounds to measure even in a squid, right? So now we have to put them in quartz, right? And whether we're subtracting the background, or whether there's some small impurity, I don't know, right? But that's not the final word on the 1 to 2s or the what we call now revised version of the 1 to 2 132. Right? Of course, we can do DFT calculations, right? And now that we know that the structure is not 1 to 2, but it's 1 3 2, right? And we can see that everything falls into place, right? You take 3 metals, right? Lanthanum, lithium, antimony, you put them together in the proper ratio, right? They form the right structure. You open up a small gap. The way it should be, right? And again, it took some effort to prove it, right? And then I had some resistance to overcome, right? But it did work at the end, right? So this paper is now published, right? So more complicated things, right? Because this was a side project, right? I started off as a summer project for undergrad, right? And very soon became obvious that a graduate student had to be involved, then a postdoc, right? So this also started off with an undergrad came to me, right? And said, well, I'm a biochem major, right? And they required the University of Delaware lab experience, right? I couldn't find a place in a lab, right? Do you have something for me to do, right? The person has not taken inorganic chemistry. And I took him, right? 2 weeks later, he comes back and says, well, I made a new compound. 2 weeks literally, right? Now this was probably the first or the second experiment that this person did in the lab, right? So he needed help with all the steps, right? Now, but this is where we are in terms of synthetic inorganic chemistry. So I don't know how many of you are familiar with crystallography space groups, right? This is a non-central symmetric orthorhombic space group with a unit cell volume of almost 4,000 angstroms. Okay. So organometallic chemists, right? Take bulky ligands and other things, right? And they make compounds that have unit cell volumes of 2,000 angstroms, right? So what I did was I took 3 metals in a very ungodly ratio, right? And I form a structure, right? So you cannot even begin to describe these structures by close packing. This is a hexagonal close pack, with certain fractions, right? It's impossible, right? So by the way, this was a flux growth, right? So butchered attempt to use indium flux to do something in the strontium antimony phase diagram. Right? So those of you that will try to use a third element to grow a binary, right? Always have to be mindful of this, right? The flux is almost never innocent. Right? So I use almost 20-fold excess of indium, right? And I have only 1 indium per 11 strontiums and 9 antimonies, right? So how would I even think about understanding the structure, right? And what does it tell me, right? So again, the Pauling electronegativity scale, right? Indium and antimony very close to each other, very similar electronegativities, most likely covalent type interactions. Strontium on this end and here donating electrons, right? So now, the structures, we'll dissect, right? We'll look at individual fragments, right? And we'll try to count electrons, right? So, this is the strontium. Again, the bonding, to other elements is not shown because we think that this is electrostatic, right? So there's no directionality, right? So this dumbbell here, right, is antimony connected to another antimony. I'm going to call this antimony 2 4 minus, which will be isoelectronic with I2. With iodine molecule. Right? So each antimony takes 2 electrons to form a covalent bond. So chemists call this reduction. Okay? Reducing in chemistry, right, usually means adding electrons, right, breaking bonds. Right? So I took in elemental antimony. Right? The distance in elemental antimony is 3.06 angstroms. and I'm standing up in front of you and I'm telling you that I reduced antimony and I formed antimony distance of 2.85 angstroms, right? I have to, shoot myself, right, if I believe this. Reduction, means, breaking bonds, right? So what happens here? Covalency, yes, right? No, antimony is a metal, right? No, the bonding is delocalized, right? No, there's no directionality, right? So by reacting antimony with strontium, right, and indium, right? You're taking those electrons, right? And you're putting them on antimony, right? You're forcing the antimony to form covalent bonds, right? Now this is a single two electron interaction between antimony, right? This antimony here is not connected to any other antimonies. We'll call it 3-, right? To complete the octet, right? It just has 6 strontium neighbors, which are almost in octahedral coordination, right?
The antimony 3- just sits between 2 dumbbells. Is that how we perceive that?
We'll see in a moment, right? So, yeah, it's a very unusual, environment, right? But this dumbbell and this dumbbell are almost 8 angstroms apart, right? So there is an octahedron that sits in between, right? So the indium, group 13 element, right, sits in a tetrahedral hole, right, almost perfectly tetrahedral, right? So how?
So the dumbbell is 2.8 this way along the bond you drew, but into the
this is 2.8 angstroms, right? From this dumbbell to that dumbbell is almost 8 angstroms,
okay.
right? So plane to plane, right? So here, right, these are perfectly reasonable, you take the sums of indium and antimony, right, the elemental and the radii, right, add them together, right, and you get almost perfect agreement. So how we count electrons here, right? So there people see this, right, even my colleagues from my department, right, and they cringe, right, what is this 9-, right, this is ridiculous. Right. But this is a formal, way of me, right, into partitioning electron, right? It doesn't mean that this thing exists. It doesn't mean that you can take it, dissolve it in any solvent, right? And, right? Just bookkeeping of electrons, right? So indium 3+, each antimony 3-, this becomes 9-, right? Or I can do something even crazier, right? I can say indium, which is a group 13 element, forced to become in a coordination environment reserved for group 14, right? Has to have a formal charge of 1-, right? To be a tetrahedral with 4 bonds. In each antimony that has 2 bonds, right? 1 bond, right? There will be charge minus, right? 4b is for 4 bonds. The 1b is for 1 bond. Right? So shared electrons, right? And reduce the charge, right? Either way, that god ugly formula, right? Breaks down beautiful. You take it, you partition it, right? Strontium cations, one of these, and 3 of those, right? Breaks down perfect. Right? Which means again, you take 3 metals, right? You fuse them together, right? Through some process, right? You form this compound, right? Which is a semiconductor. Right? In this case, here even the band gap, by calculation is wider, right? And we were actually lucky to have a sizable enough in the crystal, so we were able to measure the resistivity, and we do see in a very nice Arrhenius like activation behavior for this. Right? The problem with that, the compound was very unstable, right? And my motivation was to use this small gap in a semiconductor for thermoelectric in applications, right? So thermoelectric requires of course high temperature, right? Because we wanted to harvest energy, not to use it for cooling, right? And we decided to use now with a graduate student D metals, right? Because transition metals have higher melting points, right? So we figured that indium, being this soft and squishy thing, right? With the low melting point is maybe the reason why the compound at 200 degrees C falls apart, right? So we figured, well, manganese, we saw examples of compound that have manganese and tetrahedral coordination with antimony, right? And that would be a perfect fit, right? Again, this was not one, but 2 graduate students in their lifetimes spent on this. Right. We're going to make the manganese version of that compound, right? So of course now we cannot use manganese flux, right? Now we have to use other tricks, right? We tried, and we couldn't, right? Now we finally resorted to using periodic trends. We switched from antimony to bismuth, right? So we used bismuth flux. We made something, right? Not quite the same, right? The formula became even uglier, right? The symmetry became even lower. The unit cell became even larger. So what happens here, right? Now this is the monoclinic unit cell projected without the calciums, right? So breaking it up, right? So again, we have dumbbells, right? Now this is bismuth, right? Now again, the bismuth and antimony, they're just one above next to each other. So bismuth in the metal is 3.6, right? In this compound is 3.06, right? This is over 20% reduction in the separation between bismuths upon adding electrons, right? Extra bismuth, which is just an octahedral hole, right? Now what happens is, instead of just a single tetrahedral species, right? Now we have a tetramer, oligomer, right? 1, 2, 3, 4 manganese centered tetrahedra that the conjoined through shear edges. Right, now you will notice that there's interesting manganese separation center to center, right? This is an anti-ferromagnetic coupling between those three, right? And this is ferro to the trimer, right? So we're still debating how to describe the magnetic structure. But now if you laughed at the previous 9- charge, right? Look at this here. So this whole thing, right, this molecule, this ion, right, now will have to be called the manganese 4 bismuth 10 22 minus, right? Now because again, I'm extrapolating from the previous examples, right? This is manganese 2 plus each, right? So it should be that way, right? Or we can say, all right, so we'll now partition the bonding, right? Now each manganese behaves as a pseudo main group element of group 2, right? So now we'll have to be assigned a formal charge of 2 minus. One bonded bismuths, right? Now those guys here are going to be 2 minus, and those that are shared with 2 bonds will be called 1 minus. Either way, right? This extremely ugly formula, right? And unpleasant to even look at, right? And it breaks down to 21 calcium, 2 pluses, one of those units, 2 dumbbells, and 4 of these isolated bismuths. So again, you take the electrons, you partition the electrons, right? And you count the electrons. It looks like it's a semiconductor, and it is a semiconductor, right? Now we have to do spin polarized calculations, right? And those of you that have ever done calculations would appreciate what it takes to build a superstructure in a monoclinic setting, right? To calculate spin up and spin down, right? So it takes some effort, right? But it is a semiconductor. 21,418, right? Is a semiconductor. Yes, sir.
From the calculations, you would also get the valence electron.
Yeah, this tells you here, right? The Fermi level, right? Which we always set at 0, right? And falls in the gap, right? Which means that the number of valence electrons that we have here, right? And the way that we partition it, right? Is right. Right? And this calculation here, right? Now this is a crystal orbital Hamilton population, right? These are the bonding states, these are the anti-bonding states, right? So the Fermi level, right, crosses right in between, right? So the bonding, all interactions in the structure are completely optimized. Right. So again, I mentioned that this was 2 graduate students work, right? So I kept believing that we should make this, right? The graduate students kept telling me, no, this isn't what we make. And I refused to accept this, right? So, and I said, well, how come? There's something here, right? So lesson to be learned, right? This is what we want to make, 1119, right? I call this 2218, right? Just to show you how close we are, because this is a one-part synthesis, right? You cannot take different strategies here, right? So you put the elements together, right? And then you light a candle, right? You say the magic in a word, you hope for the best, right? So, once, twice, 3 times, change the graduate student, postdoc, right? Same outcome. So, finally I admit it, right? And I'm dumb, right? So, this is what I want to make. This is what nature allows me, right? Orthorhombic and monoclinic, right? And I just change the projection, right? And I'm showing what we should have gotten and what we got, right? The difference, right, back to your question, right? Here's, calcium in an octahedral hole between the two manganese tetrahedra, right, which are facing each other, right? 22 to 18, right? So if I take now with Photoshop the magic wand, right, and I erase this, this is the arrangement in the actual structure. If I now take, the magic wand and Photoshop, right, and I fix 22 to 21, right, I'm getting closer, right, but still no cigar, right? So what happens now here is I create a hole, right? Nature doesn't like holes, right? This is a close pack in the structure after, right? So those neighboring, free antimonies, right, come closer together to fill that hole, right? By doing that, right, what happens is you create two tetrahedral holes, right, which you can fill with two manganese, right? And then with Photoshop, right, you draw the bonds, right? Voila. Why? The bigger question, right? So again, erasing that calcium, fix the stoichiometry 22 to 21. Creating those two tetrahedral holes, stuffing them with manganese, goes from 2 to 4, right? This is the aha moment, right? I should have known, right? This is electron deficient. I'm trying to make a compound, with a prescribed structure, right, that doesn't have the right number of electrons. This one does. So, we are, roughly in the right place in the ternary phase diagram, which is unknown, right? Or if it's known, probably is incorrect, right? And because, we're close, right? Nature somehow finds a way with the same, building, fragments that I need, right? To, readapt to something that has the right number of electrons to form the right structure, right? And I'm almost done, right? And then, again, in solid state in the chemistry, right? Make a prediction, right? So impossible, right? So, right. How do you go about making a compounds in a rational way, right? Envision a compound with a known structure, unknown structure with some property, right? So this is what we wanted to make, right? It didn't work, right? We subtracted, or removed one calcium and added to manganese, and we formed this oligomer, right? So this was the stoichiometry of that oligomeric, fragment, right? That I had in my compound, right? Now I can make a prediction, right? What if, I sent a graduate student in the lab and say, well, remove one more. On paper, it works beautiful, right? You remove it, you add 2 more manganese, and you form a one-dimensional chain, infinite chain, right? This one is for the dimensionality, and the infinity symbol is the way that the chemists label those, right? 4 divided by 2 means that of the 4, right, 2 are always shared, right? And I know what the charge of that thing would be. And it would be awesome if someone can go in the lab and make it, right? And this was a struggle, right? We tried and we tried and we tried and we tried and we never made it, right? And finally, we realized that, we got the electronics right? We got the electronegativities right. Now, what we didn't get right, probably is the sizes, right? So when we got this brilliant idea, right? It took 1 week, right? Basically, we substituted calcium for sodium, right? And then manganese became aluminum, right? And the 2+ for 3+. That's why the charge here is now reduced, right? And turns out that if you're working with 3 cations, not 2, right? You can pack the exact same chains with the exact same orthorhombic structure that I wanted, right? Just with different elements. Okay. And I have more slides, right? But I'm running out of time, right? So I'll guess I'll leave it at that, right? And if there are any questions, right?
Great. Thanks, Svilen.
spent half a day in the building, right? Then the younger
And a
one,
5-year-old,
the
smashes it.
younger one got in the fist of him for something, right? And then one can smash the whole thing, right? And then you hear these little screams from the second floor, right? And the doors are slamming, right?
Yeah, that sounds familiar.
Very nice talk. Really enjoyed it.
So, yeah, I probably should share that in the 37 paper, which, you before we send it out, right? So,
Syrian business.
in the binary phase diagram, there's a 3-7 phase. So, between the 1-2 and the 1-1.
Is it interesting?
Interesting from chemistry point of view, right? Maybe because it has humongous structure.
Is it condo or anything? Is it metallic? Or you didn't study it? Send it to us.
How many? One cerium site? How many cerium sites?
Helena likes more than one.
No,
3 or 4.
I like one cerium site.
No.
GP.
The structure is a lot more complicated. It has those bismuth squares that are sort of intersecting in different. It's an orthorhombic cell, right? So it probably has at least 2 sides.
Okay, well, done.
We happen to make things that the physicists don't like.
Well, it's just very hard to explain physics that you see from more than one cerium site. Sometimes even one cerium site is not easy to explain, but more than one.
I worked, with as a postdoc in Los Alamos with Zach was not there, right? Joe Serrao was still in the lab, and Eric and Bauer, Joe Thompson. Same lab that whole work with, yeah.
Okay. Yes.